Okay, let's continue the discussion. The proposition 7.17. Proposition. Remember, we're going to write the gamma function as an integral. Okay, so we already discussed the so-called the Cauchy criterion for the convergence. Now let's define G to be the set of Z such that the real part of Z is a positive right half plane, and we define a sequence of f, which is from 1 over n, integral from 1 over n to n, e to negative t to z minus 1 dt for n greater than or equal to 1, and z in G. Okay, then the conclusion is that each Fn is analytic on G, and the sequence is convergent in H of G. Sequence is convergent in H of G. Okay. Okay, now let's see. How do we prove it? Fn of z is integral from 1 over n to n. It's actually the integral of this internal function, integrand. So f of n of z is the integral of phi tz, which is e to negative t to z minus 1. Remember, you have two variables, you integrate one, and along the straight line. Straight line segment, 1 over n and n. Okay, let me find the result we need to show it is analytic. Okay, so I don't find my textbook, but it's on page 68, the proposition 2.1. The proposition 2.1 says if you have a phi defined AB cross CD to C continuous, and if the partial phi partial t exists and continuous, exists and is continuous, then gt, which is the integral from a to b phi st ds, is continuously differentiable. Okay, so this is the result in the chapter 4, section 2, proposition 2.01. You can have this. Basically, you have a differentiable two variable functions, and then the integral is differentiable, which means you will get analytic stuff. Okay, continuously differentiable. So we get Fn is analytic. We get Fn analytic. All right, Fn analytic. Then for any compact subset, K of G, there's always a positive real number. There is a positive real number. There are not is there too. Positive real numbers A and B, A and capital A and capital A, such that K is contained in the subset Z. A is less than or equal to the real part of Z less than or equal to the capital A. Okay, this is because you have a compact subset. And since Fm of Z minus Fn of Z, it is equal to the sum of these two integrals. Okay, for m greater than n. It doesn't matter which one is greater than who's greater than who, and you just get an order. Okay, so so by this lemma, 7.16 we just showed last time. 7.16. Let me find the lemma 7.16. Yeah, this is a 7.16. So if alpha beta are sufficiently small, then this is less than epsilon. Okay, so you just need 1 because they have the order. The smaller number is greater than enough number, then the reciprocal will be less than enough. And then here is the same thing. When the smaller number is greater than a bigger enough number. Okay, this is 7.16. So by this we can see that we do have a Cauchy sequence. Okay, so we have Fn a Cauchy sequence. In where? In H of G. Cauchy sequence always converges if you have a complete space. Okay, in a complete space, Cauchy sequence always converges, and H of G is complete. H of G is complete. So the sequence Fn must converge. So here we have different. We have a small common sense. Whenever you say converges, it means you have the limit point. It is inside this. If it's not inside H of G, we will say it converges to a point outside G. Okay? If we say some sequence converges in certain set, it means it will converge to an element in this set. If it is a Cauchy sequence may not converge to the point inside it. Okay? So Cauchy sequence is a intrinsic property. It may not have the limit if the bigger space is not complete. Okay? Okay, so we do have, so we finished the proof. We do have that the limit n approaches infinity, Fn is equal to F in H of G. And this F, we will write it as 0 to infinity e to negative tt to z minus 1 dt. Or write this way. Okay? That's the stuff. So first, we define this function. And second, we show that f of z is equal to gamma of z. We're going to show f of z is equal to gamma of z. They are analytic functions. Okay, they are analytic functions. When we show two analytic functions are equal, we only need to show they coincide over certain set with limit point. Okay, so here, by the way, this part we only we assume this real part of z is positive. It's on the right half space. Okay, in order to show the equal to the gamma function, we only need to show that fx is equal to gamma of x for x greater than or equal to 1, because this set has a limit point. Once two analytic functions have agree over a set with a limit point, those two analytic functions will be equal, right? Okay, so now let's try to compute. Basically, you are going to say one is equal to the other one. Before the computation, we need an observation. It's not an observation, it's a formula. So we need the following formula. What is the following formula? Integral from 0 to n, 1 minus t over n to nth power t to power x minus 1 dt. Let's compute what this is. This computation is the application of integration by parts. So this t to power x minus 1. X is a number, okay? So this one is a derivative of 1 over x t to power x. So f dg. So it's a 1 minus t over n to power n, 1 over x t to x, 0 to n. Here, 1 over x tx. And this is you differentiate this one, you will get n 1 minus t over n minus 1, negative 1 over n dt 0n. Alright, and then you check here, when t is equal to n, 1 minus 1 is 0. When t is 0, this is 0, so this first term disappears. Here you have a negative n. Negative sign is positive, n cancelled. Or if you don't cancel it, let's just leave it. So you will have, numerator you have n, denominator you have x, you have n. And then the integral 0 to n tx 1 minus t over n minus 1 dt. Alright? Okay, now let's repeat the integration by parts. Let's keep this in. So integration by parts, we're going to move this t to x into the differential. So it's a d x plus 1 t to x plus 1. Okay, so it's n x. It's 1 over x plus 1 t to x plus 1, 1 minus t over n to power n minus 1, 0 to n minus integral 0 to n 1 over x plus 1 t to x plus 1, and then this is n minus 1, 1 minus t over n minus 2, and then times 1 over n, negative 1 over n and dt. Okay, it's a product, dt. All right, sorry, with a big bracket. Okay, again, this evaluation is 0 because when t is n, this is 0. When t is 0, this is 0. So the first part is 0, and then you have a negative sign, they're cancelled. Okay. So what do we have? We have n numerator. Here you have n minus 1. Then here you have n, here you have an n, you have n squared. This is x, this is x plus 1. Okay, negatives and negatives and cancel. So we have 0 to n. 1 over x plus 1 is already moved forward, so it's tx plus 1. 1 minus t over n minus 2 dt. Okay, so you see here, minus 2, the denominator is 2 squared. And here is n minus 1. We're going to repeat this when you have n minus n. When you have n minus n, what we have? When you have this part n times, after n times. After n times, the numerator, here's 2, you have 2 numbers. If this part is n minus n, you will have n numbers. This is n numbers. The denominator is n square, n to nth power, n to nth power. Then here you will have x plus 1, x plus n minus 1. Integral 0 to n, t2, here's minus 2, here's plus 1. If here's minus n, here's plus n minus 1 dt. Okay? So imagine that if you don't follow me, you do one more step about integration by parts. You do one more step integration by parts. Okay? You will get. Okay, so this is n factorial, and here this one we know what the antiderivative. So okay, so this is n factorial over n to n x plus 1 x plus n minus 1. This one, it is x plus n minus 1 plus 1 t2 x plus n 0 to n. So n factorial n to n x n plus 1 x plus n minus 1, no n plus 1, x plus 1. Here is a 1 over x plus n. This is n to x plus n. When t is n, it's n to x plus n. When t is 0 is 0. Okay, so n to x plus n. Here n to n. So cancel them. You will get the numerator is n factorial n to x. The denominator is x plus 1 x plus n. Okay, so you put them together. This is the formula in the book on page, where is the page number? Page 182. Well, it's not difficult, just take time to compute. Okay? Take time to compute. Okay, then we know that this formula converges to gamma of x as n approaches infinity by the Gaussian formula, by the Gauss formula. By the Gauss formula, this one will converge to the gamma function. All right, so we're going to show that this one also converges. Well, it's here. We're going to show that the limit is integral 0 to infinity e to negative t t2x minus 1 dt, which is fx. Okay, so it's needed to complete the proof. Okay, so if we can prove this limit is also equal to fx, then everything is done. Everything is done. Okay, so the issue, what is the issue? The issue is that they change it together. They change it together. Okay, So now let's prove. Let's prove this. Okay, to prove this, we form it as the next dilemma. The next dilemma has two parts. Part one, it is integral 1 plus z over n to power n converges to e to z in h of g. The first one. And the second one, if t is greater than or equal to 0, then 1 minus t over n to power n is always less than or equal to e to negative t for all n greater than or equal to t. So for n bigger enough, it's always correct. Okay, so technically, when I learned the mathematical analysis, we learned this by definition. We first prove this limit is equal is a finite number, and then we define it to be e. That's that's how we learned the initial the starting point of e. But here we don't do that. Okay, we don't do that. We are going to prove it at this moment. Okay, so let K for the part A. Let K be a compact subset of the plane. K is a compact subset of the plane. Then every compact subset of the plane is always bounded. Then there is a natural n such that absolute value of z is less than n for all z in K. It's just because K is compact, it's bounded. Okay, it's bounded. In order to show this limit is equal to e to z, it's sufficient to show that we take the natural log n log 1 plus z over n is equal to z. Same thing, uniform. For z in K. Uniform for z in K. Okay. Well, let's do it. Log 1 plus w. We do have expansion. Log 1 plus w is equal to K from 1 to infinity, negative 1 to power K minus 1, w to K, not K factorial. Okay, it's a 1 plus w. And of course, this expansion, Taylor series expansion, has limited domain. Okay, so we need this w with modulus less than 1. So let n greater than modulus of z for all z in K. Then this n log 1 plus z over n. You see, z over n has modulus less than 1 because of this condition. So it is equal to 1. K is a 1, so it's n. K is a 1, this is a positive, so z over n minus z over n squared over 2 plus z over n cubed over 3 minus dot dot dot. Right? So you multiply it by n. What do you have? you have z minus 1/2 z squared over n plus 1/3 z cubed over n squared and minus blah 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 stuff. Right? And then let's try to compute the difference between those two expressions. So n log 1 plus z over n minus z, it is equal to this tail. This tail, you see that you just have this additional z, copy of z every time. So we factor out z, we will have negative 1/2 z over n plus 1 over 3 z over n squared minus 1 over 4 z over n cubed and plus 1 over 5 stuff. Right? And then we take up's value. We compute the distance. Take up's value. It is going to be less than up's value of z, and we apply the triangle inequality. We will have sigma k from 2 to infinity 1 over k z over n to power what? K minus 1. Power k minus 1. Right? 1 over k, it's at the most 1/2, so we amplify it. We drop that 1 over k. K minus 1, so k is from 1 to infinity. Z over n. K. Oh, this is k, my bad, not 1/2. This is k. Okay? And this one is a geometric series. So now it is a geometric series. So it's the leading term over 1 minus common ratio. Leading term over 1 minus common ratio. So it's equal to z squared over n up's value times 1 over 1 minus z over n up's value. Okay, now let's try to estimate it. You see here, k is compact. Set k is compact. Then up's value of z is less than or equal to r for some r. For some r. And all z in k. Okay, so the numerator will be less than r squared over n. The denominator, you see here you have z. Z is increasing function. With a negative sign, it's decreasing function. With you flip it, it's still increasing function, right? You have a z itself is increasing. Up's value of z is increasing function. You put a negative sign, it becomes decreasing function. You compose with the reciprocal, it's still increasing function. So it's going to be less than r squared over n times 1 minus r over n. Right? So that's the way we find the maximum value. Of course, I can do it step-by-step comparison, but you will have the same thing. Increasing, decreasing, and increasing again. Okay, so what this is, you do the computation, it's r squared over n minus r. You do multiplication. This r is fixed for k. R is fixed. N can be as large as possible, so n will be essentially eventually greater than r, approaching infinity. So if n approaches infinity, the difference goes to 0 uniformly. For z and k. So we do need it approach 0 uniformly. We don't just need the pointwise convergence. Uniformly. Okay, if it's uniformly, then we can see that the function, the sequence of this analytic function converges to e to z. because this one is converges to Z. Okay, remember we're talking about the convergence in H of G. In H of G, how do we determine a sequence converges to another analytic function? We just say over every compact subset, the sequence uniformly converge to the point, converge to that analytic function. Then it is convergent in this sense of H of G, right? Okay, very good. So this is a part A. Part B. Part B. Part B, we're talking about, where's part B? Okay, here's part B. We're talking about the comparison. Okay. Let me copy it here. T greater than or equal to 0, 1 minus T over N to power N is less than or equal to e to negative T for N greater than or equal to T. Okay, we want this. So first, we have this formula. Where is it? This one. We have this formula. We just need negative T here, not a Z. So we have N log 1 minus T over N and minus Z minus negative T plus T. It is equal to this one, negative T and sigma K from 2 to infinity. Okay, now let's see 2 to infinity what we have. If you have, you see, it's very good. Z is negative T, negative T, negative sign, they'll cancel. Z is negative T, but squared, there's no negative sign. Z is negative T, cubed is negative sign, with this negative sign cancel. So there's no negative sign. It's excellent. So it's a 1 over K, T over N to power K minus 1. Right? So by coincidence, this negative cancel, this negative cancel. Alternating sequence series becomes just positive series. This is always positive, and with times negative T is less than or equal to 0. And be careful here, we require, when we have this expansion, we require this this case. We require N greater than ups value of Z. In other words, we have the condition T is less than or equal to N. Actually, strictly less than, strictly less than, strictly less than. When T is equal to N, there's nothing you need to compute. When T is equal to N, this left hand side is 0. 0 is always less than 1, right? So here we can actually drop this equal sign, because you have, when you have equal sign, you don't have the expansion, Taylor series expansion. Well, on T is then negative 1. Yeah, negative 1 is okay. Negative 1 is alternating harmonic series. Let's avoid it. Let's avoid the equal to N case. Okay. So this means what? This means N log 1 minus T over N is less than or equal to negative T. Less than negative. And then you apply exponential function. You apply the exponential function here and here, you will get the result B. You will get the result B. Okay? So that's a case. Okay, very good. Very good. So we finished the proof of a 7.19. 7.19. We get the preparation, and in the next video, let me see if I can finish it. Well, let's try. Let's try if we can finish it. Okay, so we finished the 7.19. Now let's back to proof 7.15. We start to show. We start to show f of z x is equal to gamma of x. We start to show this. Okay, so here we assume x greater than 1. It doesn't matter. We fix this. We put this condition. We don't lose any generality. Okay, so fix x greater than 1 and epsilon greater than 0. Fix epsilon 1, choose epsilon greater than 0. Then we can find a k greater than 0 such that for r greater than k, integral from k to r e to negative t to x minus 1 dt is less than epsilon over 4. It's a 7.16, I believe. It's a 7.16. The result we proved the last time. And let n be an integer, any integer, greater than this k. And let fn be the function defined in proposition 7.17. So what is fn? Fn is this is fn. Remember, this fn is a from a Cauchy sequence. It will converge to the point. Okay, so this is fn. It is defined over the right half plane. So we have fn of x. We don't use z. We use x minus integral from 0 to n 1 minus t over n to power n t to x minus 1 dt. We just compute this, right? We had before the 7.19. We have this integral converges to gamma of x, gamma of x, right? We have this long computation, integration by parts. Okay, so let's try to see the difference. What's the difference? Difference here is from 1 over n to n. Here is from 0 to n. Right. So if it's from 0 to 1 over n, you don't do any subtraction. You just copy the second term. If you have from 1 over n to n, you actually have e to t minus 1 plus t over n well, first of all, let me see it. Okay. Yeah, I think this part is negative sign. It's not positive sign. It's a mistake. In the book, it is a typo. So it's a subtraction. It's a subtraction. Okay. Because here's minus. Here's minus. All right. Remember when n is sufficiently large, n is very, very big. When n is sufficiently large, we have this integral from 0 to 1 over n, 1 minus t over n to nth power t to x minus 1 dt. It's going to be less than or equal to this expression. This is the part B of propositions lemma 7.19. This one is less than e to negative t times t to x minus 1 dt. right? Because here, in this case, this t is sufficiently small, so for whatever n you can apply it. We only need n greater than t, but in this moment, t is between 0 and 1 over n. T is very, very small. Right? And this one, this integral, remember it can be smaller than any given epsilon by the first part of the 7.16. So here we need sufficiently large n. For sufficient large n, we just make sure this one is small enough. Right? This one is small enough. And this is one condition for the sufficiently large n. For the other part, by part A of the 7.19, by part A of 7.19, remember we have the convergence of value of 1 minus t over n to power n minus e to negative t. Convergence, it will be greater than or equal, less than or equal to epsilon over 4mk, whatever, there's some constant here, 4mk. For t in 0k, where is the k? K is here. K is the bigger number, very big integer. You can just take integer. So for t over this compact set, no matter how big it is, it's compact. Okay, for compact set, and m is the integral from 0 to k t to x minus 1 dt. It's a fixed number. We remember we fix x. We fix x, k is selected, then this is fixed. Actually, we know what it is, right? This is k to power x over x. Yeah, this is such number. Bad power. It's not bad. Okay, so we do have this. We have this, and we make something and choose this n sufficiently large. Choose this n sufficiently large. Okay, then we're going to control the second part. We're going to control the second part. So the integral from 1 over n to k. Here's from to n. Let's amplify it to k. Amplify it to k. So e to negative t minus 1 minus t over n to nth power and times t to x minus 1 dt. So first you put the ups value inside. And then this one is less than epsilon over 4mk. And this integral is m. You cancel this m. So you have, why do we need this k? We can even make this bigger. They change it, replace it by 0. So 4mk times m. I don't see where we use this k. Where we use this k. Okay, let's leave it here. I don't think we use this number k here in the denominator. So we do have epsilon over 4k, not epsilon over 4 in the book. Okay, this is a okay. So far, let's check here. We have, let's see what we have done. We are going to compute this, we are going to estimate this part. This part is from 1 over n to n. But n is greater than k. K is selected. K is fixed by this property. Then you choose whatever n greater than k. So far, this part, you only cover from 1 over n to k. You don't cover from k to n. So we need to get the coverage from k to n. From k to n. From k to n, the strategy is the following. So first, we move up's value into it. And this one, by the triangle inequality, is going to be less than twice of e to negative t to x minus 1. And this n is greater than k. Remember that for whatever r greater than k, this is less than epsilon over 4 times 2 is less than epsilon over 2. It is less than epsilon over 2. Okay? Okay, now I see what is I see what is the problem here. Okay, I think I understand which part is a mistake. This m setting is not this. Let's check here. We replace m by the maximum of t to x minus 1 over 0k. Maximum of t to x minus 1 over 0k. I don't care what value it is, it's a maximum number. And then you have this, you're going to replace it by the maximum value and integral from 0 to k dt. The maximum value from integral from 0 to k is just a m times k. And then this time you can cancel m with k. So this textbook has something misleading. This is the definition of a capital M is not the integral from 0 to k t to x minus 1 dt. It's just maximum value of t to x minus 1 from 0 to k. Okay? Because x is greater than 1, so this is always well defined over 0k. Just find the maximum value. I don't care where it is. Okay? It could be whatever. I really don't care what it is. It's a continuous function over complex set. Maximum value always exists. Okay, now it makes sense now. So m is a maximum of t to x minus 1 over the closed interval 0k. Over the closed interval 0k. Okay? So what we have fn of x minus integral from 0 to n 1 minus t over n to power n t to x minus 1 dt. Remember, we have 3 parts. Originally, we have 2 parts. This part, but this part is decomposed into 2. So it's going to be less than or equal to 1 epsilon over 4 plus epsilon over 4 plus epsilon over 2. This part, ops value less than epsilon over 4. This one, the first part is less than epsilon over 4. This part is less than epsilon over 2, so it's less than. It is equal to epsilon, no equals. All right, so we get the limit n approaches infinity, fn of x minus its integral 0 to n, 1 minus t over n to power nth power, t to x minus 1 dt. It is, the limit is equal to 0, and it is equal to fx minus gamma of x. And in this process, we do need assumption x greater than 1 because this function is continuous function. Otherwise, we don't have this. All right, very good, very good. So we do finish the proof. The gamma function is equal to this fx, the gamma function is equal to this, and for the over the right part, over the right part. Right? There's application. Yeah, I can finish. So we have 0 to infinity, e to t to 1/2, negative 1/2 dt. Let's discuss this application next time. Okay, so we finished the proof. Very nice, very nice. Okay, thank you. We stop this video. We will continue the argument of this in the next one. Okay, thank you very much.